5 minutes per hour.
Okay. Or we wait for another.
Yeah. Or go and bell, put a banner. You can just go and shout.
बुलाया ताली बजाया
ठीक है, आ जाए. इतने लोग 4 बजे हैं, ये बहुत.
हाँ.
Perfect, perfect. Hopefully you'll also enjoy. Hopefully you'll also enjoy. I'll make you wake up. Fingers tend to feel cold. The body doesn't feel cold. The fingers tend to feel.
They are morning better. चालू करें? Will we start? Yes, yeah. To the final session for the day. Our last speaker is Professor Rahul Vaze from TIFR Mumbai. So Rahul did his master's from IISc Bangalore. I don't know, long back, I guess. And then after that, he has been a faculty at the School of Computer Science and Technology, I guess, at TIFR Mumbai, and he will be speaking on this topic.
All right, thank you. And happy to see many of you at 4 p.m. It's been a long day. And hopefully, will be all pictures here. So if any picture is not clear, please raise your hand. More than happy to stop and tell you what's going on. So this is joint work with Abhishek. The first part of work is mostly his work. The rest I'm going to talk about is something new which we are doing now. And again, it's the final part actually will be only pictures. So hopefully it will not be too much as we touch 5 p.m. All right. So I don't think all the Google guys have disappeared. So I wanted to just thank them for sponsoring the work. The work would have happened, but the generous grant was very helpful. So here is a very simple convex optimization problem everybody sees and encounters. So what do we have? We have a function f, which is convex, and you want just simply to minimize the usual convex optimization. So I'm going to put the online spin to everything. So let's just make this online now. So what is online here? It's now time is going to be discrete and the total capital T time slots. Before anything is shown, you're going to supposed to pick an action A1. Once you pick that action, I'm going to tell you the loss function. It's a very terrible setting to think about that. First your action is picked, then you're telling me a loss function on which you're going to evaluate my action. And this continues sequentially. So every time you pick an action, thereafter I tell you the loss function. What do I care about? That all actions should belong to a bounded set. So everything is going to be nice. Sets are going to be bounded. All f's are going to be convex as well as bounded. And all the information I'm going to reveal, even after the action has been taken, is the value of the function evaluated at the action or the gradient of that function evaluated at the action you chose. That's all the information we are going to reveal. We're not going to give you the full function. That's too much to ask. Even though it is delayed, even then we are not going to give you that. All I'm going to give you is function evaluated the action and the gradient, which is again evaluated in the action you've chosen. And they're also one step behind. So first you choose the action, then I reveal the function. Sorry? Yes. Convex bounded, everything is nice. All right, so what is a benchmark? So supposing you knew all the functions ahead of time, what you wanted to find was an optimal static action. So this action is not allowed to change across time. So single action, if you could pick knowing all the functions ahead of time, is your benchmark. All right. This is called a static benchmark. There's also dynamic benchmark. I'm not going to talk about dynamic benchmarks in this talk, but many of the things can be extended, not everything. So this is essentially a single optimal action knowing all the functions ahead of time. And what do we care about is regret, which has been repeatedly defined. So I'm going to define it one more time. So this is the benchmarks loss function evaluated at the optimal action. So this is going to be typically smaller than the loss I'm going to incur under my information model, where action is chosen before function is shown, and the only information given is the function evaluated the action and the gradient evaluated the action. And what do I want to care about is I want to minimize this, which has been in the worst possible choice of functions FTs as long as they're convex. All right. So this is what is defined as the static regret for this problem. So this essentially at this point, you should think about this is a hopeless problem. I am asking you to pick actions, then I'm going to show you functions which are allowed to be chosen adversarially. You should not be able to do anything reasonable. But surprisingly, what you can show is that this quantity can be made to scale as square root t instead of t itself. See, t would have been trivial. So if it is going to scale as order of t, because everything is bounded, that's trivial. You pick any action. One second. Any action is going to give you an order t regret. Interesting question is, can you get square root t? And you can, yes. So you just take, so supposing you have an adversary who has access to what actions you're taking, he's going to pick functions knowing what actions you're going to take. So his objective is to maximize your regret. Knowing that, your objective is to minimize the max. Bounded, that's all. Yes. Otherwise, lots of nonsensical things will happen. Overall, t going from 1 through capital T. So you're allowed to choose all the bad ones. I don't get to choose, you get to choose. So I'm going to, essentially, I'm even revealing the action. So I'm doing the action first, then you're giving me the function. Yes. So over all functions from 1 to capital. Yes. Differentiable at that point. Yeah. But yeah, we'll give that for free. All right. So now the interesting question is, what algorithm can achieve square root t? And here is a very simple algorithm which does it. It's called online gradient descent. So we all know what gradient descent is. All this is going to do is, you look at the previous action, which is a of t minus 1. You look at the gradient of the function which has been most recently revealed to you, evaluate its gradient at the previous action, and eta t is the step size. So all you're doing is you're taking one step along the gradient of the previous function shown. That's all the algorithm is. So here is a simple schematic of what is going to happen. So at time t, I don't know what the function ft is. All I get to see is ft minus 1. Actually, I don't get to see all of ft minus 1. All I'm going to use is the gradient. So all I do is I look at where I was at time t minus 1. I take one gradient step along the direction of gradient of ft minus 1 with a step size of eta t, and that's my new action. And you can actually choose eta t independent of everything else as just 1 by square root t, and you can show in few lines of proof that this gives you a regret of order square root. So here is a more detailed illustration of why it actually works. So now let's suppose we'll instantiate this. So all the odd functions are x square, and all the even functions are just translated x minus 10 whole square. Again, the algorithm doesn't know any of this. It's just going to see how the algorithm is going to behave on this particular input. It's a very specific example chosen to show, in the worst case, how is the algorithm actually able to achieve square root t like this. Okay, so now it's clear that the static optimal action is actually x star is equal to 5. So remember, the benchmark is allowed to only choose one single action. Because these functions are symmetric, it turns out easy to even see that the optimal action, in fact, is always play x star is equal to 5. And now let's start from any particular point to run the algorithm. So even is some arbitrary action, let's take it to be on the left side of 0. So I'm going to evaluate this, and that's my first real action taken by the algorithm. At this point, the gradient is pointing this way. I'm going to take eta to be 1 and then move to this direction. So this is my going to be action A2. At this point, I will look at the red function because I'm one step behind. So when I'm taking action at time 2, the only function available to me is function f1. So I'm going to go along this direction. So I'm actually going away from x star. But eventually, so this point is essentially along this blue curve somewhere very high. And at this point, I'm taking the gradient. So I now come back, and this algorithm just keeps essentially moving around x star is equal to 5. Sorry. So this is what the trajectory, if you plot this trajectory as a function around x star with a step size of 1 by square root t, this is how it oscillates and converges towards x star is equal to 5. This is a very simple schematic of what happens in the static setting when you apply the online gradient descent. So this is a good time where I'm going to take a pause for a second, and any questions? Yes. OGD still is okay. You just have to define the regret differently. It's actually, if you think about it, the dynamic problem is slightly easier. It's a non-trivial statement, but think about it. So that's not something I know, but there is FTRL which works. So that assumes the knowledge of all the previous functions, and you find a static action which minimizes the sum of all the previously known functions. That also gives you the same result. No, I don't think constants are any different, because there you have to introduce a regularizer. That seems to be having some, what is it called? Sorry? Yeah, so no, so if you don't add the regularizer, it changes the actions dramatically, and you don't get the right regret. So you have to additionally add a penalty term called the regularizer, which makes sure that the per step movement is not too large. Slightly. Okay, so that's an exercise for all of you. Find your problem and map it to this. It's as universal as that. So I'm not going to talk about any applications today, because it's so universal. If you think for 5 minutes, you'll be able to map your problem you thought about ever to this. All right. Okay, so this is essentially all background classical work, textbook stuff. All right. Now we come to really the interesting part. So now, if you take any convex optimization class, 90% of the time we talk about unconstrained stuff. This exactly is the intuition. So if you look at so this example is chosen to be as bad as the example for OGD, where these the alternate functions are as far apart. So 10 can be made 100,000, doesn't really matter, because as soon as you push this away, the x star also goes towards the middle of the two. So this, sorry, this is, I want to show that picture, and a little bit of delay in there. So this picture is essentially all there is to it, what OGD is trying to do. rate at which you're choosing eta t to scale as 1 by square root t is really at the heart of it. So it's not just going along the gradient, but going along at the right rate is very important. No, so that is chosen because of the chosen the choice to be symmetric. You can slightly disturb them, and wherever that X star is, it will automatically center itself. So if you think about it, this example is almost the worst case. I can't prove it, but intuitively, this is as bad as it can be for the gradient descent algorithm. Okay, so now let's go to the constraint case, which is more interesting. So usual again, in the constraint optimization, you have F convex, this set is constrained, and you would like to find the minima among in the given constraint set, which is also convex. So now I'll take the online version of it. So as before, this is as before. You pick an action, then a loss function is shown. What is new is also I'll go give you a constraint of the type g1x to be less than or equal to 0. So action is chosen, then the loss function comes, and simultaneously also give you constraint. So before, you're incurring a loss because you chose an action. Now you're also incurring a constraint violation. Because you're choosing an action before I show you the constraint, very likely you're going to violate it. If you're lucky and don't violate it, you just take a 0. Otherwise, you violate a constraint, and I'm going to charge you g1 of a1 as a violation. And this process continues at time t. Once you choose an action, this is the loss function and this is the constraint. And as before, we're going to assume that both ft's and gt's are bound. So this is all the notation I'm going to use. Ft is the loss function, gt is the constraint function. If you can remember, please try to remember. That's much easier. If you add them together, what I'm going to do is going to be much harder. If you add them together, it becomes a new convex function, and everything which we said before is already applicable. So we have the more interesting case to keep them separate. And as before, once you choose the action, ft's and gt's and their gradients are going to be released. Okay, now one constraint. So this is again a problem formulation. If you don't like it, you can generalize it. What we're going to assume is for the benchmark, something happens. So look at the intersection of all these constraints, and we're going to look at the set of the intersection of all these constraints and assume that that set is non-empty, essentially to ensure that the benchmark does not have any constraint violation. That's all we really care about. So the benchmark is allowed to play an action which minimizes the loss functions subject to x belonging to this set, which is the intersection of all the constraints. If you don't like that, you can generalize it. You can allow the benchmark to also commit some constraint violation, and then you can compare again. But for the moment, I'm going to assume that the set of actions that satisfy all constraints is non-empty. So every single constraint across all time slots, a single action can simultaneously satisfy all those constraints. So there was no x belonging to S. So that's the only difference. See, because you're one step behind, that's not clear. That's the problem. So yeah, so that's not the correct intuition. But one might want to think about it. So both of them are tied very closely. That why the gradient is good enough is because you're moving towards x star, but not necessarily. See, as I showed in the example, so in consecutive over a large period of time, I get pushed towards x star, but not every time. I actually get at certain time slots, I get pushed away from x star. Yes. Okay. I don't remember there is any such guarantee. No, it's not well behaved. Yeah, it's not that. Yeah, it's not as simple as that. Sorry. So just keep in mind that this is important. That the set of actions that satisfy all constraints are non-empty, and the benchmark is only allowed to play one such action, which minimizes the sum of all the loss functions. If you don't like this and you would allow violation, so essentially it keeps the violation for the adversary or the benchmark 0. That's the point. All right. just come. So you can think of it as, let's say this is my base convex set from which I can take my actions. So the first set which is going to be shown is set of axes for which g1 x is less than or equal to 0. The second function might be of this type, but because I'm requiring my x star to belong to all such consecutive functions, I can essentially take the intersection. So instead of looking at g's, which are defined as sets of all x's for which gt is less than 0, I can just look at the intersection of them. So I can define S1 to be G1, S2 to be essentially the intersection of G1 and G2. So what I end up getting nicely is that STs are nested. That's the good property I'm going to exploit, that the consecutive sets I'm going to look at which are feasible are sitting inside each other, and all of them are convex. So that's a good thing to remember for the rest of the talk. That the sets which are getting revealed over time, I'm going to call them STs, and ST is sitting inside ST minus 1. And this progressively essentially shrinking, and all of them are convex. No, so this is called a nested convex body. So in the convex body literature, this is called a nested convex body problem. It will come up soon. But there is a function associated which you want to minimize. That's where all the problems start to appear. So in the constraint set point of view, this is what, if people know, this is called as the nested convex body field. All right, so now let's come to how I'm going to penalize. So regret is as before. So regret is the loss you're incurring compared to the loss the benchmark will make, where x star belongs to the feasible set S. And now the maximization, or the worst case I'm choosing across both FTs and GTs. So the adversary is allowed to play bad FTs and GTs. I still want to control the regret. And the violation is as defined as follows. How much violation do I make at time step t is GT evaluated at ET, and I sum it across all time. If at certain point I happen to be feasible, I just count 0. And I want to control both of them simultaneously. If I were to add these two things together, my job would be actually simple. Then you can just use the machinery of what I described, unconstrained online convex optimally. And the difficult job is to control them. Okay, so this is a good point to, again, take a moment's pause. If there are any questions on the problem formulation, very important. At least the problem should be clear, if not the solution. Yes, so S is the set which the benchmark is allowed to play, which happens to be the feasible set of actions which are feasible to all the GTs which are shown across time. So G1 is shown at time 1, G2 is shown at time 2. Pick a feasible solution to all of them, take the intercept. You're not allowed to see anything. This is just hidden assumption somewhere, that there exists a set S which is non-empty, which satisfies all the constraints simultaneously. That's all. So the algorithm doesn't get to see anything. Over here, second one, okay, so you can remove that. Yes. You don't see it, SX to L. Yeah, correct. GT of 80 only. Yeah, let's keep the square root t away. I want to control them simultaneously. So it's a two-dimensional problem I want to raise. Yes. It got us nowhere. I will tell you, most people have done that, and I'll tell you what guarantees you can get using that. That's the first thing you would try. People try it. See, at the end, the message I'm going to detail at the end is you're spectacularly failing at understanding this problem. So keep that in mind. So don't expect any optimal answers from me. You've done something, it's interesting, but you're far away from understanding even the simplest of the problems. Yes. All right. So I'm going to detail what is known for this. So we gave the name COCO. It was known by constraint online convex optimally. But this COCO is quite bitter. All right, so it's roughly 8 years now, yeah. So this was, I think, more or less the first result. What it showed was an algorithm which can get you a square root t regret. So this is common theme that the square root t regret is easy to achieve. All the interest was in how much can you control the violation penalty. So this result gave you 3/4. Then Neely came along and he said, okay, if I have a Slater's condition, if you don't know Slater's condition, it's okay. All it says is there exists a point strictly in, so X star happens to be in the strict interior of S. If you don't know, it's okay. Then under that condition, you can actually get square root t, but there is something dividing that, which is essentially how far away from the boundary you are. So it's actually effectively not a square root t result, but the way it is stated, this is what it is. Then there was another result with a very different algorithm, which appeared a couple of years ago, which again got you square root t and t to the 3/4. This was slightly more general. So as a function of beta, it gave a full range that if you want a particular beta to regret to scale as max of beta comma minus beta, you can get a violation penalty of 1 minus beta by 2. But if you instantiate the best one, so if you wanted square root t regret here, you will again get back 3/4. So this essentially we are stuck at square root t and t to the 3/4. And there is no fundamental reason for any of these. That why simultaneously you cannot do anything better than that. So major open question for many years was, can you actually achieve simultaneously a square root t bar? That was the, so surprisingly, people thought that's the question to answer. And the take home message at the end of it is there's nothing fundamental even about this. Even if you achieve this, you should not be happy. We're going to achieve this, but we're not happy about it. All right, so without any conditions, what you want to achieve is both the regret and the violation penalty simultaneously scaling as square root. So this was the result which we proved last year now, because Neurops in December, that one can actually do that. And let me go to the approach, which was slightly different than the usual approach one would try by putting a Lagrangian. So here is a very simple description of our approach. So CCV is nothing but constraint violation, cumulative constraint violation. So you count it until time t minus 1, and this is the due violation. So you're choosing an action 80, it got evaluated at GT of 80. So that's the new violation you're going to make. So I'm just keeping a running sum of how much I have violated so far. No, then we point 0 anyway. So we don't allow any credit if we are strictly feasible. It's either 0 or positive. Maximum. So that's why I'm only counting this. If it's feasible, then I just count it. Yeah. See, the OCO lower bound is actually very specific because it's allowing you unconstrained access to what function you can choose. Once you put constraints, that doesn't apply to. So it's even without nestedness, that doesn't directly apply. So regret you can show is square root t, because suppose there are no constraint and you get a square root. But as soon as you impose a constraint, even square root t is not a lower bound. So it could be that you can, so if you're ready to accept a square root t violation, it could be that t to the 1/4 is a regret. It's possible. So what I'm going to do is to combine the loss function at time t, which is ft of x, plus this violation evaluated at a function. So phi is a function, convex function, prime is a derivative, and you multiply it at the violation you accrued at that particular time t. Just that. Okay. And phi is a convex function. So I'm just defining a new surrogate function for myself to run unconstrained OCA. It's not a Lagrangian, but this is behaving like a Lagrangian. So this is the weight I'm assigning to my Lagrangian. If you think about it, this is the loss function. This is the constraint. Only at that point, I care about the constraint violation across all time. So I'm multiplying some weight, which is evaluated at the derivative of a convex function, evaluated at the total penalty you've seen so far. Yes. CCVT 0 is just evaluated 0. So if this already is 0. So if, see, this is an increasing function. all of this is 0. So I don't care. You'll see only everything in pictures. So, yeah. Okay, so that's the function I'm going to work with and apply the usual OGD algorithm. So I've thrown away the constraint. All I've done is taken the loss function, added something from coming from the cumulative violation, and now thinking of this as my new function, which is unconstrained. And you just apply your online gradient descent. Don't use eta t simply as 1 by square root t. Use something what is known as adaptive. What if you know ADA grade, it's okay, but something to depending on the gradient value. That's all. So algorithm conceptually is the same algorithm as before. I've done nothing else except change the function on which I'm playing the ADA grade. That's all I'm. So in pictures, this is what is going on. So suppose at time t, you're feasible. So it should be AT, sorry, it's not the XT. So AT is the action and happens to be feasible at that point in time. Then all I do is look at the new function that has arrived and take one gradient step. That's all I do. I forget about any violation that I've accrued so far. I don't care. Everything is out. If otherwise I'm infeasible at that point in time, then I look at the surrogate function. So I might add ftx plus the surrogate part and then take the gradient descent, and that's my new action. These xt's should be ATs. So there is no xt essentially. So the action I'm taking, if I'm feasible, only depends on the loss function I'm shown. If I'm infeasible, then I combine the two and take the gradient. Sorry, eta t is a step size, which is no. So the gradient, it's part of the gradient descent routine. So this is the function on which I'm taking the gradient descent. That's all. Okay, so now why does it work? So this is the choice of phi we are going to take. Okay, you can play around with phi. So phi is nothing but exponential x by square root t essentially. And phi prime, you will essentially get this constant out. That's all will happen. So it will look like, the new function will look like 1 by square root t e to the power. Not too large. So how large is the question? So it has to become square root t log t before the constraint starts to come. So that's exactly the intuition about this algorithm. So it essentially behaves in two phases. So until the constraint violation happens to be little o of square root t log t, it's as if this is being forgotten. All I'm doing is feasible, infeasible. All I'm doing is gradient descent on the function shown. So I should expect a regret of square root t until this point. Once it hits that, then it suddenly changes track and starts to look at this part of the function and starts to forget this part. So now all the action is on the constraint violation. But again, you should thinking of GTs as functions. Now this is doing OGD over the constraint functions. And again, you should get a penalty of no more than square root t. So once you already accrued square root t log t, you should not expect to spend more than square root t thereafter. But the interesting question is, in the second phase, what's happening to the regret with respect to FT? Does anybody see why that should be controlled intuitively? No, so there you did whatever, but now the second phase could be very long. The point is the constraint set are nested inside each other. So if you are trying to minimize this CCV, so this picture will help you. So now the set to which I really care about. So X star is my feasible action, which is sitting inside this nested sets. And if I'm caring about the second phase, I'm essentially pushing towards this set. So even if my functions, I did not care about the FT loss functions, I'm moving towards X star because I'm not paying any more penalty than square root t log t. My comparison is with respect to only X star. So even if I'm not paying any attention, I'm actually going closer to X star. So X star could be a bad choice for minimizing FT, but my benchmark itself is bad. So now I'm getting closer to benchmark. I might not be going closer to the minimizer across the full set S1, but I'm getting closer to the minimizer of the smallest set possible. That's essentially the this one or the next. Sure. No, no, you want how much it is. So see, the gradient will come from here. So if GTX is so if you're infeasible and you're far away from the feasible, it's bounded, but still how at speed at which it's going to go depends on how large GT is. So the gradient of GT has to appear somewhere. Indicator is not alone sufficient. See, when you're taking the gradient of this, so forgetting this part, this is just a constant factor. The next picture or the previous one? This one? Okay. We'll come to that algorithm, wait. Gradient of G is right here. So this one. So this is the function I'm applying OGD on. So this is nothing but a constant. The gradient of GTX is appearing here. So assume that this is 0. How I'm moving? This is the weight at which I'm moving multiplied by the gradient of GT of x. So I'm getting closer to the x. True, but you also want to look. So if you do not have that, at least the analysis will not work out. The intuition might. That's fine, but where am I coming from? I'm coming from the outside. So at least I'm moving towards S. And the convex function, even though it might not be moving to the optimizer, it's more likely to be smaller compared to where I was outside. So it's not precise. That's true. So it need not be that you exactly get to the X star. You might be coming around, but overall, you'll be coming closer to X star. So S could be large. So exactly, that's the intuition. The math exactly is not this way. So intuitively, you should think about why it is not disturbing the regret in second phase is that my benchmark itself, I'm getting closer to the benchmark. Benchmark could be bad. Could be, but you're coming from a worse because you're outside, you're at least moving towards the right direction. Sorry, phi? Yeah. So phi is this and phi prime is capital T is the time horizon. So capital T is known ahead of time. So time horizon is known. This is the function we are playing ahead of time. There is lots of things hidden inside. So it's you can think of it as multiplicative. So initially we tried with, as usual, squared Lyapunov functions. It gets you t to the 3/4. Suddenly we realize if you just substitute, so this is actually a general formulation. This you can get an answer in terms of phi. Then when you plant the appropriate phis, you start getting different answers. So the usual choice is always the square. It got us only t to the 3/4. Exponential suddenly gave us the right. Yeah. Yes. Because when will this factor be useful? When the CCV happens to be square root t log t. Otherwise, this is very, very large and all this is very small. So unless this part becomes more than square root t log t, this plays no role. So that's why until square root t log t, the second factor is actually dormant. It's not doing anything. It's only all the attention is to ft. Yeah. Yeah, because now GT I want to minimize. So the gradient of GT is moving towards minimizing GT. And this prefactor is much larger than the prefactor over here. So then I start paying only attention to GTs, F tags along. And because exactly, and because the benchmark is sitting there, That's the intuition. All right, so this is how you get to the constraint violation of square root t log t and the regret of square root. Yes. The gradient of GT and gradient of FT, they are kind of pointing. No, not necessarily at all. But FT might be telling us you to go outside of S, but your benchmark is S. That much you know. So GT is pointing towards the benchmark. That's the bit. They could be completely opposite of each other. And that's what we'll essentially. So given the time I have, so I'll skip this. And yeah, let's just, I'll tell you what the limitation of all prior approaches, including this one is. So why square root is actually a bad bound. So what really happened was we treated both FTs and GTs as functions. We did not really care about the constraint set coming from GT as a convex set, which is shrinking. We did not actually paid any attention to that. And here is a simple example. So think of your functions being constant. So ft is just f of x. So for every time, the function is just c times x squared, where c is very large. Okay, every time I'm going to show you the same function. I'll give you ahead of time this function. And this is my feasible set. The feasible set is between 1 and a is very large. And with respect to gt, the feasible set is going from a by 2 to a. Now, it's an obvious thing that the optimal action should be to play a by 2. That will minimize the regret as well as constraint violation of 0. But the algorithm which I just told you will actually get you a square root t regret and a square root t violation on this simple instance, because it doesn't care about any of this. But this is a very concocted problem given to, if I keep changing FTs, then nothing of this will work. I don't know. Then the performance is very good and what you're doing is kind of. Yeah, I don't know. So hopefully this example tells you that this algorithm which I'm doing, so let me, given the time, let's just see how you will execute my algorithm. So this is the function I'm going to play. So suppose my first action is here. I'm going to disregard the feasible set with respect to GT until I hit a constraint violation of square root t log t. All I care about is how large is my function here. So I keep moving towards minimizing this function, going up farther and farther away from the feasible set. So until I accrue a penalty of at least square root t log t, I'm going to care about this function. And then I start going towards, yeah. So then I start going back towards the feasible set. And in the process, I get a non-zero regret and a non-zero violation penalty, while this instance was actually very simple, where you could have simply chosen a by 2 and the problem was solved. So this is the real limitation of all the approaches, that what they did really was they treated FT and GT as functions instead of functions and convex sets. So all we're going to say is the following. So this is the nested body, nested convex body chasing problem. So what is that you want to do? So suppose you're given a point x0 to begin with. I'm going to show you a convex set. And all I ask is move either inside or on the boundary of the set. That's all the constraint there is. So suppose you move somewhere, then I show you the next body, which is necessarily sitting inside the first body. Then you again move. Let's say you go to the boundary and you keep doing this. What is my objective function? My objective is to minimize the total distance I move, such that I have to be feasible at each point of time. So this is the objective. The total distance moved should be minimized as long as you can satisfy the constraint that xi belongs to. So this is a very well-known problem. Almost optimal answers are known for this problem. So one simple example is to move to the centroid. So as soon as I show you the body, you just move to the centroid of the body shown. What it does is, essentially, I will not move from this point until you show me a body which is significantly smaller in volume. That's the point about the centroid. That if I'm moving to the centroid, x1 will become infeasible to s2 only if s2 does not contain x1. And now think about where can you place it. It has to necessarily So this is a feasible body, so I'll not move. It has to necessarily become shrink in sufficient volume, and there is Grunbaum's lemma, which tells you that at least it shrinks by half. So that's the idea about this algorithm, and gets you a total constraint violation of order d log d. You can do something simpler. You can simply project. So instead of going inside, you just go to the boundary, but go to the projected point. So x0 will get projected to x1. Again, take the projection on s2 and so on. This is now more interesting, pays a larger distance, but this is a very interesting convex geometry paper, which shows that the total distance you travel in this is at most d to the power d by 2, where d, remember, is the dimension of the problem. I'm doing this capital T times, but there is no dependence on capital T. Essentially, the distance is somehow shrinking and it's not large enough, so you get a d dependent bound. This is larger than previous. That is d log d. This is d to the power d. Point is, you cannot do centroid in our setting, so you'll have to live with something like this. Okay. So this motivates our new algorithm, and I'm going to stop after that. I don't want to overshoot. So here is the new algorithm. What it does is the following. See, I don't have this simple problem of nested convex body. I also have to worry about the function f. So what do? So suppose my point was, first action was x1, and this is the body shown. This is the violation I'm going to incur. I look at the function you're going to show me. So I first take a gradient descent step from this point, and then I project onto the set which is shown to me. And every time I just do the same. First take gradient, project. Take the gradient, project. It's not a good idea. You can do it, yeah, but it's not a good idea. No, so anything which you go inside, what can adversary do is to keep pushing you back to the boundary. So there's no reason to actually go inside the body, because the choice of f's given to you will be in such a way that they're minimized outside. So there's no point going inside. So this is the algorithm, that every time you see an action and you are infeasible, you first take a gradient descent step and then you project onto the next body. So for simple convex bodies, I can show you what we can derive. So the regret of order square root t is immediate. You don't have to work very hard. It directly follows from the usual analysis. All the work you have to do is on the violation, because remember, you're not simply, so this curve is not a connected projected curve. So earlier what I was showing was x1 just gets projected here, and I project this point back to x3. Here I don't get to do that because I first have to play a gradient descent. So I'm going arbitrary directions on this convex set. So that's the difficulty I have in trying to upper bound the total violation. Earlier, I was simply taking projections after projections, consecutive projections, and that's why the distance was d to the d by 2. Now I don't have the handle of how far I am going or which direction I'm going. So that is why an immediate answer doesn't show up. But for simple sets, so suppose these SIs are in 2D rectangles, then what you can show is that if the violation is of distance L, the diameter of this set at least has to shrink by L by square root D if I were to travel a distance of L. So if I am accruing a violation of L, the diameter is at least shrinking by L by square root D. So if you put it together, the total violation you cannot be more than D to the 3 by 2 times the diameter of the problem. So this is a very simple example. Something similar you can do for spheres. Almost identical you can do. That if you travel a distance of L, you'll exactly shrink the diameter along one of the D axis by L by square root D. They are totally D axis. Every time you're putting square root D, so putting that together, you get a T independent bound. But the punchline is that you can get a T independent bound for sets are nice. What happens when sets are not nice is really what the difficulty is. And I think I'll just stop at this point and convey the message that it's possible to get a T independent bound with a small caveat, which we can talk offline. So the punchline is the square root T regret is achievable, as well as a T independent violation is achievable, but it's not that simple. So it depends on what the convex bodies look like. So it depends on the shape. So it's an instance dependent answer is what you can get. Depending on these shapes of these convex bodies, you can get an answer in terms of that. which is independent of the time horizon. But it's spectacularly failing everything because we don't have any matching lower bound or even idea for simple uh, instances of the problem, which is as follows. So suppose I freeze a function f initially. So ft is f, and f is given to you ahead of time. Only thing that is changing is the constraint set. Give me an algorithm which does better than this. It's as simple as that. So single function with respect to which you want to minimize the regret, and constraint sets are arriving one after the other. You want to minimize the regret as well as the constraint violation. Can you do better than this? It's not clear. No, they're nested. The function, they're not changing across time. So I give you the function ahead of time, reveal the full function to you. Tell me what is the regret you can achieve and what is the constraint violation. Yes, constraints are convex, they're nested and they're shown online. The function, the loss function I'm giving you ahead of time. And you just want to minimize the regret with respect to loss function and the constraint violation with respect to these ones. This is much simpler than what I was trying to solve. It turns out we have no better answer for even for this simple case. Sorry? Yes. No. So, so geometry is used to get the final answer, but we're not using segment to project. One could project in any twisted space, but we're not doing that yet. Yes. So that is a standard projected grade. So what can happen is, even if you are this unconstrained problem and you are only given one single set on which, so it just simply follows. Yeah, it's kind of non-intuitive, but that works out. So that math is very simple. It's the play on the violation is where all we are spectacularly failing. No better answer. So unless they have very nice structure like not even polytopes, axis parallel polytopes one after the other, I can give you an answer. No, yeah, half spaces are as bad as what we. So we get, so I didn't want to go there, but we get an answer in terms of the instance. So you give me the instance, I'll give you as a function of that instance an answer, which is t independent. But you can choose the instance in a bad way and somehow make it behave something like even larger than square root t. So best lower bound, it also was surprising that there was no such thing and we derived one. The best lower bound we have is square root d, where d is a dimension, and a square root d. So there is no dependence on t in the lower bound. If you think about this problem, it's very weird. If you're ready to accept the constraint violation of square root t, it is not clear that the regret should be square root t. The regret could be much smaller than square root t. That's the problem with this formulation. So the best algorithm I know is when you go to the, it's a generalization of the centroid, Steiner points. Yeah, so Steiner point gets you slightly better, but again, the Steiner point is inside. So for our problem, going inside is definitely bad. So you should not be going inside is pretty clear, because I can choose functions and push you back to the boundary. So all your wasted effort is not going to help you. So even there, even if the function is fixed, it could be the minimizer is outside. Now what do? You keep going back. So it's essentially a welcome. I'm done. So it's essentially an open opportunity for anybody to solve this problem. And somebody is asking for applications, just go back home, think for a second, you'll find 10,000 applications for this problem.
Somebody is waiting for talk to formally get over and ask, are there any questions? Okay. Thank you.